We will try to understand that how a PM interaction diagram for non-rectangular section can be developed. So first we will take a circular cross section. Okay. We are going to take a circular column of diameter 500. Okay. Where D dash is 50 and diameter is 500. So 50 by 500, that is 0.1. Percentage of steel we are taking is 2. The total number of longitudinal bars is equal to 8 numbers of 25 dia bar. So AS turns out to be 3925 square. Okay, so that is exactly 2%. So ratio of percentage of steel by FCK, that is 2 by 20. FCK we are taking as 20 is 0.1 and F5 we are taking as 415. Sometimes it so happens that we don't have programs for different non-rectangular shapes column, then we can do the analysis manually and also get the value of ultimate load and ultimate moment carrying capacity of the particular section for a particular depth of neutral. If you are making a program, then it is good to subdivide the area of the cross section into 1 thick strips. Okay. Say I'm taking my neutral axis at 250 mm. Then if I'm writing a program, then I can divide this area into 250 strips. Okay, that is thickness of strip equal to 1 mm. That will give me more accurate results. But as we are doing it manually, we will subdivide into few strips. Okay, so over here, this detail is shown because we are given interaction diagram, interaction design interaction curve for circular column in SP16, and we will also cross check our results with that. So this is the diagram which I have taken from SP16, where D dash by D is 0.1 and F5 is 415. Okay. Now all this interaction curve are for the ratio of PT by FCK. Our ratio of PT by FCK is 0.1, so we are taking this. This is a very important table given in SP16 known as table A, where you can find the stress for the corresponding strain. Okay. Now, if the bar is in compression, then whatever stress you get from this table has to be deducted by the stress of concrete, that is 0.447 FCK. If the bar is in tension, then Fs will be equal to F5. Whatever value of stress we get from this table, we have to directly take it because in tension zone, we neglect concrete. So we will be using this table number of times. Now, first of all, let us draw the actual whole PM interaction diagram for this column section. So there are 5 number of steel layers. Number 1 at 50 mm, number 2 at 108.578 mm, uh, steel layer number 3 at a distance 250 mm, steel layer number 4 that is at 391.422 mm, and layer number 5 that is at 450 mm. Okay. So we will draw a complete interaction diagram first and then we will check our results. Okay. Okay. So we will take the circular section first. Okay. Let us select the section. Okay. WD, that is diameter of the section, is 500 mm. Press enter. Okay. Effective cover we are taking as 50 mm. Press enter. Number of steel layers are 5. Press enter. Okay. The first layer is at 50 mm and the area of steel in that layer is 490.625 mm square. The second layer is at 108.2 578, and the area of steel is 981.25 mm square. The third layer is at 250 mm, and the area of steel is 981.25 mm square. Fourth layer is at 391.422, and the area of steel is 981.25 mm square. The fourth layer is at 450 mm, and the area of steel is 490.625 mm square, right? F5 we have taken is 415, F6 is 20. Let us assume the design load is 1200. Okay, press enter. Design moment is 100. Okay, press enter. Now let us draw the PM interaction diagram. We'll use this option too. Okay, so this is the interaction diagram, PM interaction diagram for the circular section. And this is the table, okay? Complete analysis for different depth of neutral axis. Okay, so sorry, let us start with the first case. Okay, when the neutral axis is at 250 mm, we will be dividing this area into three uh, strips, okay? And we will see that the result which we get from this manual calculation will be very much near to the exact calculation. Maybe the results may differ from 5 to 8% only. Okay, so this is the strain diagram. Okay, the strain on the outermost concrete face will be ultimate strain will be 0.0035, and strain on the tensile phase will be 0.0035 into d minus xu divided by xc. Okay. Now this is our stress diagram. Okay, when the neutral axis is in the uh, column section, then we know that the stress diagram will be similar to that for the flexure member, right? So we know this is our concrete design stress diagram. Okay. Now we also know that up till strain 0.002, that is depth 3xu by 7, over here it is 107 mm, the stress remains constant. Okay, that is the stress will be 0.447 fck up to over here, right? Over here the strain is 0.002. Okay, now so we will divide our area into three strips. Okay, first strip will be a segment. Okay, and this segment will, the depth of this segment we will take up to 107, where the strain is 0.002 and the stress is constant in this area, right? So this is how we'll get force FCC1 for this segment. Now remaining two strips, we will have equal depth, that is 71.5 and 71.5. Okay, so this is how we will get three forces. One force due to this area, another force due to this area, and third force due to this area. Okay, FCC1, FCC2, and FCC3. So we have assumed that compressive force we are taking as positive, and anti-clockwise moment will be taken as positive. Okay. So FCC1, FCC2, and FCC3 are the force due to concrete design go, and all the three are compressive force, so all the three will be positive. Okay. Now we know how to find the area of the segment. Okay, okay, and we also know how to find the CG for this segment, right? So FCC1 force falls at a distance 63.235 from the compression phase. Okay, so let us find the force FCC1 first. So FCC1 is 0.47 FCK into area of this segment. Okay, so that will give you force 275.27 kilonewton. Okay, so once you know this force, you can find the moment. This is positive because this is compressive force. Now this will give an anti-clockwise moment about CG, and this distance is 250 mm, and this is 63.235 mm. So that will give us the moment force into 0.25 minus 0.0632 35, and that is equal to plus 51.412 kilonewton meter moment. Okay, this is anti-clockwise, so this is positive. Right? Now let us find the force FCC2. For finding the force FCC2, first let us find the mid width of rectangle strip. Okay. Assume to be rectangle strip. Okay. So this is the mid width, and for the corresponding uh, for this corresponding width, find the strain from this diagram, right? So the strain turns out to be 0.0015. Once you know the strain, put the value of the strain in this formula, that is strain by 0.002 whole is to square, and this is 2 into strain divided by 0.002. This strain is 0.0015. So we get a value of Fs. Over here, we get a value of Fs equal to 0.419 FCK. Right? So we can now find FCC2. So FCC2 is equal to 0.419 FCK into depth of the stream 71.5 into width of the stream 451.625. So this turns out to be 270.616 kilonewton. Now we know this distance. You can find this distance, and you can find the moment which is going to be anti-clockwise. So this is going to be positive. This force is positive because it is compressive force. Okay, so this is positive. Now this will give an anti-clockwise moment which will be positive. So force into 0.25 minus 0.14275, which is equal to 29.03 kilonewton meter. Similarly, find force F CC3. So this is the width. Corresponding strain is 0.0005. Put the value of strain over here. Fs we get as 0.196 FCK. So FCC3 is 0.196 FCK into height of the strip, okay, 71.5 into width of the strip, that is 494.86. We get FCC3 is as 138.7. Now you can find the moment like this. Okay. So FCC3 into 0.25 minus 0.21425, and this is the moment 4.96 is positive because this is anti-clockwise moment, right? So this is how we have found all the three forces due to concrete design curve, right? Now we have to find forces due to the steel layer. There are five steel layers: layer 1, layer 2, layer 3, layer 4, and layer 5. So there will be five forces: Fs1, Fs2, Fs3, Fs4, and Fs5. This is our neutral axis. Okay. So these two forces will be uh, under compression, and this will be tensile force. Right? This force will be positive because they are compressive force, and this will be negative because they are tensile force. Okay. How to find Fs1? Simple. Find the strain, okay, from the strain diagram. So the strain is found to be 0.0028. Okay, this is for Fs1, right? Once you know the strain, and you can always use this table. 0.0028 falls between this. You can find the stress. Okay. Now we know that the steel is under compression, so we will have to use this formula. Whatever stress we get has to be directed by 0.447 MCK. Okay. So our final stress is found to be 343.19. Once you know the stress into area of steel in that layer, will give you the force. Now this is compressive force, so this is positive, right? Now this force will give a moment, anti-clockwise moment about C. This distance is shown over here. Okay? Distance from CG, that is 200. So this distance is 200, right? So force into distance will give you the moment. This force is anti-clockwise, so moment is positive. Similarly, find fs2, find the strain. If the strain turns out to be 0.002. Once you know the strain, find 0.002 falls between these two values, find the stress, okay, as the steel is in compression, so you will use this formula for finding Fs, right? So the final Fs is found to be 320.06. Stress into area, that is area in this steel layer, okay, will give you the force into this distance will give you an anti-clockwise moment, and this distance is uh, 141.422 mm. Okay, that turns out to be 44.14 kilonewton meter moment. Positive because it is anti-clockwise. Okay. Now coming to this force, it is on CG. Okay, so force is zero, and moment will also be equal to zero, right? Now coming to this layer of steel, that's FS4, find the strain. Okay. Now please remember this steel is under tension. Okay, it is in the tensile zone. Okay. So whatever strain you will get over here, the strain count is 0.002. Okay. So whatever stress we get for 0.002, okay, we have to directly take it. Okay. We don't have to detect this stress for the concrete in that, because in tension zone we neglect concrete. So whatever stress we get from the table, we directly have to apply over here, right? So this is minus because this is tensile force. Okay. So this stress into this area of steel will give you the force, tensile force, so negative, right? Now this will give an anti-clockwise moment. So though the force is negative, but as the moment is anti-clockwise, the moment will be positive, right? So this distance is shown over here, minus 141.422. Moment will be positive, force will be negative, right? Similarly, Fy is negative because it is tensile, and this will give a anti-clockwise moment, so the moment is positive, right? So now when you add all these forces and all this moment, you get the ultimate load and the ultimate moment carrying capacity of the section when the neutral axis is at 2. So this is the actual value which we get from the table, and this is which we got manually. Okay, so you can see the difference is 3 to 4%. Okay, so there is no such vast difference. You can also you can do the analysis manually too. Uh, the error will be say around about uh, 5 to 8%, like that. Over here it is say 3 to 4%. Right? Okay, now let's check this on the PM interaction diagram given in SP16. MU is 243. Okay, MU is 243. Okay, and we are taking this graph, that is PT by FCK is 0.1. You get corresponding P. You can check. Okay, India. Okay, coming to the second case, we take our neutral axis at the out. Okay, say XU is equal to 500 mm. Right? So this will be our strain diagram. This will be our stress diagram. Okay, and as following the same fundamentals as seen above, we will take the first force FCC1 for this element. Okay, that is for a distance 3x by 7. Okay, that is 41 mm. Up till here, the stress is constant. Okay, the strain over here is 0.002. Okay, now the remaining parts we will divide into 4 strips, 1, 2, 3, and 4. Each of is 71.5, 71.5, 71.5, 71.5. Right? Okay. Now, so we will have 5 forces due to concrete design: FCC1, FCC2, FCC3, FCC4, and FCC5. So let us find FCC1 first. It's simple. 0.44 okay, into area of this segment, okay, will give you the force, right? Now, from the formula of the segment, we find the CG that turns out to be 124.19 here. And so this will give an anti-clockwise movement. Okay. So force into 0.25 minus 0.12419, that gives us 90.2 Newton meter. Now let us find force FCC2. So find the mid width, we are taking 500. Find the strain corresponding 0.00175. Put the value of strain over here. Find Fs is 0.440 FCK. Fc2 is 0.440 FCK into 21.5. That's the height of the strip and width of the strip. Okay, that is 500. So this is how we get force FC2, FCC2. Okay, now this will again, our CGA is at 250, this is 249.75. So this will give an anti-clockwise moment. That is equal to 314.6 divided 0.25 minus 0.24975. That is equal to 0.0786 kilonewton is a moment. Okay, both these moments are positive, and both these forces are positive. The forces are compressive, and the moments are anti-clockwise. Now coming to the third force at FCC3. So find the mid width and corresponding strain is 0.00125. Put the value of strain over here. You get Fs as 0.384 FCK. So FC3 is 0.384 FCK into 71.5 into width 47479.263. Okay, you get force FCC3. Now this will give an clockwise moment. Okay, this is at 321.25 and CG is at 250. Okay, so it will be the moment will be negative, right? 0.25 minus 0.322125. Okay, so this is how you get the force in the respective moment. Now FCC4. Okay, find the mid width, strain, stress, that is 0.272 FCK, 0.272 FCK into 71.5 into width of the strip, that is equal to this force 159.65. Now this will again give a clockwise moment. So 0.25 minus 0.39275, that is equal to minus, because it is clockwise moment. Okay. So that's minus 22.49. Similarly, FCC5, this is the stress 0.105, and this is our segment. Okay, so this 0.105 FCK into area of this segment will give you the force. Now CG is known, we can we are assuming to act at the CG. So FCC5 turns out to be this 7.75 kilonewton. This is minus. Okay, so this is also clockwise moment, so it is minus. So this is how we got the five forces due to concrete design stress diagram. Now we have to find the forces due to the steel layers. Again, five forces: Fs1, Fs2, Fs3, Fs4, Fs5. Now, as the neutral axis is over here, all these forces will be compressive. So all the forces will be positive. Okay, so same fundamentals are applied. Okay, for finding Fs1, find the strain. Strain is 0.032, right? The, uh, find the corresponding stress from the table, and as the steel is compressive, is under compression, so you will have to deduct the stress due to concrete. So this is the final stress. This stress into area of steel gives you the force. This is positive because this is compressive. This force will give an anti-clockwise moment. That is, distance of this force from the CG is 200, right? So the moment is positive, right? Because it generates an anti-clockwise moment. This will also generate anti-clockwise moment. So positive. This will generate zero moment because it is on the CG, so zero moment. This will generate a clockwise moment, so negative. And this will also generate a clockwise moment, so this is right. So these are the distance on these forces from the CG. Okay. So when you add up this, you get total PU 2473, total MU 95.4, negative 2471, and MU 67. Okay. So the difference is not much. Okay, you can see. Now we can plot this on the graph. You can see the PU interruption diagram. Okay. So when PMU is 97.4, you get 240, 2470 or something like that, right? You can take it. Now coming to the third case, when the neutral axis is out of the section, column section, we are taking the neutral axis at 750 mm. Okay, then this will be our strain diagram now. Okay, this strain will now vary between 0.0035 and 0.002. Okay, and this is our least strain, right? We know at a distance 3d by 7, okay, the strain is 0.002, which remains constant, and this point acts as a fulcrum. Okay. So this is our strain diagram now. Now this is our actual stress diagram for this case. Okay. But we can take an average stress diagram like this. Okay. So instead of 0.447 FCK, it will be some X FCK. So first find G. G is 16 divided by 7XU divided by T minus 3 whole raised to square, which is 0.2844. Put the value of G over here, you get X as 0.243. So this is how we get this, right? Now once we get this stress, then we have to find the distance J, where this FCC1 falls. So this is the formula, and we get this as 239.77 mm. So in this case, we only have one force due to concrete design stress diagram, that is FCC1. Okay, so how to find FCC1? Simple. FCC1 is equal to 0.423 FCK into area of this circular section. That will be the force. We know this force is acting at this point. Now this is 239.77, which is less than 250. So this will give an anti-clockwise moment, right? So force is compressive, so positive. Moment is going to be anti-clockwise, so it will be positive. So force into 0.25 minus 0.23977, it gives 17 kilonewton meter moment, right? Now then again, find the forces Fs1, Fs2, Fs3, Fs4, Fs5. Same steps to be followed, as all the forces are compressive, so all are positive. This will give an anti-clockwise moment, so positive. This will give an anti-clockwise moment, so positive. This will give a clockwise moment, so negative. This will give a clockwise moment, so negative. When you add this up, P is 2824 and M is 39. Actual is P is 2842 and M is 35. Okay, so very little difference is there in actual and manual calculation. Okay, so you can always do the manual calculation without some error, maybe 4 to 5% or 6%, right? So let us plot this on the graph. Okay, and use 35, you get the PU 2845. Now coming to the last case, that when n falls at infinity, we know that strain will be constant for the whole cross section, that will be 0.002. And we know when the strain is 0.002, then the stress will be 0.447. Okay, and you can see, you can check the FCC1 will fall exactly on the CG, that is 250. So this will give a zero moment, right? You can find FCC1, that is 0.447 FCK into area of this section, that is your force, moment will be zero, and you can see that as these layers are equally distributed on both sides, this will create a zero moment, right? The final moment will be zero, okay? And when you add up these forces, you get 3006 kilonewton, and actual is found to be 3000 kilonewton, right? So we can see on the graph, okay? Okay, when moment is zero, you see that this graph ends at zero point 0.6 PU by FCK PD square is equal to zero point 0.6, that is equal to 3000, right? So this is how this graph has been developed, okay, in the code. Okay, so this is how we try to understand the fundamentals which I use for drawing a BM interaction curve for a circular section. Now we will try to see that how a PM interaction curve can be developed for. Okay. So we are taking a I section. Okay. There are 18 numbers of 20 dialongitudinal bars. Okay. FCK is 20, F5 is 415. So this is 230, 230, 230, total is 690, 230, 230, 230, total is 690. Now we will divide this I section into two parts, and web. So this shaded portion is top flange, this shaded portion is bottom flange, and this non-shaded portion will be taken as web. Okay. So we will have two stress diagrams. One is for flange and one is for web. Okay. So first of all, let us draw the actual PM interaction curve for this section, right? Okay. So let this section. Okay. WD. WD is total depth, that is 690 mm. Press WV is the width of F, that is 230. FB1 is the width of top flange, that is 230. FB2 is the width of bottom flange, half flange, okay, 230. Then FD is the thickness of flange, okay, that is 230. Effective cover is 50. Number of steel layers are 5. The first layer is at 50 mm, and the area of steel in that layer is 1256 mm square. Second layer is at 180 mm, area of steel is 1256. Third layer is at 345, area of steel is 628. Fourth layer is at 510, area of steel is 1256. And the last layer is at 640, and the area of steel is 1256. Phi is 415, FCK is 20. See, our design load is 1200 and design load is 100. So we will draw the PM interaction diagram for this I. So this is the curve, and this is the complete analysis. Now we will see how can we do it manually. So taking the first case, okay, our neutral axis is at 250 mm, okay. So this will be our strain diagram, similar to that in flow, and this will be our stress diagram for this top flange, okay. Below neutral axis, concrete is neglected, so there will be no stress diagram, concrete design stress diagram, okay. So this can be now converted into an average stress diagram. So this is 3 by 7, that is over here the strain is 0.002, and the remaining portion is 122.86 mm, right? This total is 230 mm, right? So using the formula, okay? Okay, please remember over here XU is 250. Over here XU is 250. And this you have to take as DF, okay? So DF is 230, okay? So you have to take over here XU as 250 and DF as 230, okay? So we get G as 0.753. Put the value of G over here, you get X is equal to 0.3828, okay? 0.3828 FCK. Okay. Now putting all this value and we find J, that is 101.24. So this force acts at a distance 101.24. Okay. That is FCC1. Now force due to this web. Okay, so this is our stress diagram. That is for rectangular section, right? So 0.447 FCK. FCC2 will fall at distance 0.416 XU, which is 104 M. Now let us find the force FCC1. FCC1 is stress, okay, into 230. This is 230 into length of the flange. Total length minus the width of the bed. So 690 minus 230. So this is how we get the force FCC1. That's 810 kilonewton. Now this force will give an anti-clockwise moment. Okay, the CG is at a distance 345. This is 690. Half of that is 345, right? So 810 into bracket 0.345 minus 0.10124. This gives a positive moment because the moment is anti-clockwise and this force is compression, so positive, right? Similarly, find FCC2, that is 0.362 FCK, 230 is the weight, and XU, okay? XU is 250, okay? So 230 into XU, that gives 416.3 kilonewton. This will give an anti-clockwise moment, that is 416.3 in bracket 0.345 minus, this is 104, so it is minus 0.104, okay? So this will give you 100.32 kilonewton meter moment. Positive because it is anti-clockwise, right? So this is how you got both the forces that are raised due to the design concrete stress strain diagram, right? Now we have to find the forces in steel layers. Layer 1, FS1, layer 2, FS2, layer 3, FS3, layer 4, FS4, layer 5, FS5. Okay. Now our nucleus is over here. So these two forces will be under compression and these three forces will be under tension, right? So finding FS1 fundamentals are the same. Find the strain. Strain is 0.0028. Okay. Now it's compression steel. So whatever stress you get that from table, you have to deduct it with the concrete stress, that is 0.447 FCK. So this is your final stress, right? This stress into area of steel in this layer gives the force, right? Force, sorry, right? This is positive because this is compressive. This is positive because this is compressive, right? And these are the distance from the CG, right? So this force will give an anti-clockwise moment, and this distance from the CG is 295, right? So a force into this distance gives a moment. This is positive because this gives an anti-clockwise moment. Okay. This also gives an anti-clockwise moment. So positive. This still gives zero moment because it is on the C, so zero. Okay. And this force is tensile. Okay. So find the strain. And the strain is 0.0036. Find the stress from the table. Whatever stress you get, please directly apply over here. You do not have to deduct any value from the stress because it is under tension, right? So this force into this area gives, sorry, this stress into this area gives you the force. This is negative because this is tensile, right? This is also tensile. This is also tensile. So all the three forces are negative, right? Now This will give an anti-clockwise moment. So though the force is negative, but moment is anti-clockwise, so it is positive. This also will give an anti-clockwise moment. So moment will be positive, though the force is negative. Right? So when you add all these forces and moments, you get PU 824.13 and MU 622, and actual value is also found to be there, almost right. Coming to the second case, okay, when the neutral axis is at the bottom face, that is XU is equal to 690. So this will be the strain diagram, okay, and this will be the stress diagram for flange, top flange, bottom flange, and for the back. Okay, so we will have three forces: FCC1 due to the top, FCC2 due to the bottom, and FCC3 to the back. Okay, we again know that for a distance 3D by 7, the strain 0.002 will be over here. So the stress will be constant in this region, that is 0.447 okay. So this turns out to be 295.71, and this is only 230. So in we will have a rectangular stress diagram with stress 0.447 FCK. Okay. So this FCC1 will fall at 115 on the top. Okay. Now coming to the bottom flange. Bottom flange, we will have a stress diagram like something like this. It will be parabola, right? So we will have to find the stress at this level. Okay. So at this level, find the strain 0.00116. Find the Fs from by this formula. So that turns out to be 0.368 FCT. Now you can easily find force FCC2 because we know this is parabola. So using the formula, okay, 2 by 3 into 0.368 FCK into 230 into the length, that is 690 minus 230, right? So that gives you the force FCC2, that is 519.12. Once you know this force, this will give you an clockwise moment, right? So that is equal to 0.345 minus 0.54625, which is equal to minus 104.47 kilometer meter. So this is going to give a negative moment because it is clockwise. Now coming to FCC3, this is same for the rectangular section as we consider in further. Okay, so the CG of this FCC3 is 0.416 XU, that is 287.04, right? So FCC3 is 0.362 FCK into 230 into 690. This is 230, XU is 290. Okay, so this is how you get 1148.98. C3 positive because now our CG is at distance 345, and this is at 287.04, so it will give an anti-clockwise moment, right? So the moment, right? So this is how we found the forces due to the concrete design curve and their moments. Now coming to the forces, same, okay? There will be five forces: Fs1, Fs2, Fs3, Fs4, Fs5. Okay? All the forces are compressive, so they are positive, and this force will give an anti-clockwise moment, so positive. This force will give anti-clockwise moment, so positive. This will give a zero moment, right? Because it is on the CG, right? This will give a clockwise moment, so it is negative. This will give a clockwise moment, so it is negative. So when you add this up, you get BU 3950 and MU 323, which we get the actual value too, right? Okay. Now coming to the fourth case, that when the neutral axis is outside the section, that XU is equal to 900 mm, then this will be our strain diagram. Okay. This is least strain EU. This strain will vary between 0.0035 and 0.002 up to at a distance 3D by 7. The strain will be 0.002, and this will remain constant. This will act as a pivot. Okay. So this is how we get the stress diagram, right? This is the stress diagram for top flange, concrete design stress diagram for the bottom flange, and this is a concrete design stress diagram for the web. Okay. Actual stress diagram will be something like this. Okay. Will be something like this, right? Because the neutral axis is outside the section, so we can convert this into average stress diagram, which we have done over here. Right? We have converted into average stress diagram. Right? Okay. Now we know that 3D by 7 is greater than 230. Okay. So for this top flange, the stress will be 0.447 HPK. Okay. And this is equal to 230. Right? Now we will find the average stress for the web. Okay. So you can find by this formula. XU is 900, D is 690. You get G 0.4275. Put the value of D, you get X as 0.411 FCK. This is how we get stress. Now find J. J you get 323.25. Okay. So this is the CG distance of FC3. Now we will over here the distribution of stress will be something half parabola. Some part of the parabola will be cut below this. So we can take this average stress over here also. Okay. So this is how we find FCC2. Now let us find FCC1. FCC1 is 0.441 FCK into 230 into 690 minus 230. That is this plus this, right? So this is force 945.85. Now this will give an anti-clockwise moment, so positive. This is how we get the positive moment. Now FCC2, right? So it is 0.411 FCK, okay, into 230 into length. This plus this, okay, 690 minus the length, right? So you get FCC2 is equal to 869.67, and this will give a clockwise moment, so the moment is negative. Now FCC3, this is equal to 0.411 FCK into 230 into 690, right? So this is how you get FCC3. That is 1304.5 kilonewton. Now this is at 323.25 and our CG is at 345. So it will give an anti-clockwise moment. So it is positive, right? Similarly, finding all the forces fs1, fs2, fs3, fs4, fs5. fs1 will give anti-clockwise moment, so positive. fs2 will give anti-clockwise moment, so positive. fs3 will give zero moment, so zero. This will give a clockwise moment, so negative. This will give a clockwise moment, so negative, right? So adding all these forces in moment, we get Pu is equal to 4688 and Mu is equal to 128, which almost matches with the exact value, right? Okay. Now taking the last case, that is when the neutral axis falls at infinitive, then we know the strain is constant for the whole cross section, that is 0.002. So the stress will be like this. This is the stress for top flange, stress for bottom flange, and stress for the web. Okay. Stress will be constant because we know when the strain is 0.002, the stress has to be 0.447 FCP, right? And the strain is constant over whole cross section, so the stress will be also constant for the whole cross section, right? So FCC3 falls exactly on the CG, so it will give a zero moment. You just have to find the force as it is compressive, so it is positive 0.44, sorry, 0.447 FCK into 230 into 690, okay, and moment is zero, right? Now FCC1. FCC1 is equal to 0.44 FCK into 230 into 690 minus 230, right? So this is your, sorry, this is your force, and this will give a anti-clockwise moment, so positive. FCC2 will be same as FCC1, and also it will give a clockwise moment. So forces are same, and moment are same but opposite in direction. So this is minus. So, okay. So when you add this moment, you get total moment zero. Okay, that is due to the complete design stress diagram. Similarly, for the forces due to the steel layers, okay, Fs1, Fs2, Fs3, Fs4, Fs5, all these are compressive force, so they are going to be positive. Okay, we can see the strain is constant. In each layer of steel layer, you get strain as 0.002. Okay, so this proves that the strain over the whole cross section is 0.002. Okay, so this is how this force Fs1 will be equal to Fs5. Okay, we can see all the forces Fs1 equal to Fs5, Fs2 equal to Fs4, and this is Fs3, right? As this will give anti-clockwise moment, anti-clockwise moment, clockwise moment, clockwise moment, which will be equal and opposite in sign. So the total moment will be zero. Okay. So this is how we get the total force. Okay, when the neutral axis is at infinity, then we get the maximum compression force that the column section can carry, which is found to be 5112, and which also matches with the octave. Okay, so this is how these are the basic fundamentals for development of PM interaction diagram for non-rectangular sections. You can have edge section, cross section, or elliptical section. The fundamentals remain the same. You can also do the manual calculation. It's easy, and take 7 to 8 points. Can draw and also can draw a interaction diagram, and even calculation done manually is found to be much closer to the actual value. So this is how uh, I think I have made my point clear that it is easy to do the analysis or draw a PM interaction diagram for any non-rectangular sections also. Hope you must have found this video useful. Thank you.